Good afternoon and welcome to the Lunch and Learn of the 6th Annual Web Conference of the Geo-Institute of ASCE. This is Elizabeth Cusino of the Geo-Institute, and I'm very honored to be able to introduce Jim Guillory. He is the Chief Engineer at Keller and holds a Master's from Geotechnical Engineering from UC Berkeley and his PhD from UC San Diego in Earthquake Engineering. He has over 20 years experience, and he will be giving us an overview of the most common ground improvement methods for liquefaction. Jim, thank you.
Okay, great. Let me get my screen sharing started.
Okay.
Is that working?
Looks good to me.
Good.
We will be taking questions at the end of the session. Please submit your questions through the Q&A if you are watching on Zoom, or through the chat if you are joining us on YouTube.
Great. Well, thanks everybody for joining, and I'm really honored and pleased to be making this presentation today on liquefaction mitigation. And without further ado, we'll get right into it. So here's a little outline of the agenda. We're going to talk about the key elements of liquefaction, then some of the common ground improvement techniques for liquefaction mitigation, and then how we go about designing those ground improvement methods, and then we'll have some time hopefully for some questions and answers. So I kind of need to assume that most of you have some familiarity with liquefaction, and I just want to point out three critical aspects to liquefaction evaluations, liquefaction hazard evaluations. First, we need to evaluate if the soil composition is amenable to liquefaction. So we typically think of clay-like and sand-like behaviors, with sand-like behaviors being prone to liquefaction. And I'll talk a little bit more about that in a minute. Then secondly, if it's a sand-like material, is the state of that material loose enough, and is the earthquake loading big enough for liquefaction to be triggered? And then finally, if it liquefies, what are the engineering consequences or the effects of the liquefaction? So let's dive into these three aspects a little bit. First of all, we like to think of soils in liquefaction evaluations as either sand-like or clay-like. And there have been several criteria that have been proposed, some by Bray and Sancio with a cutoff at around a plasticity index of 12. Idris and Boulanger suggested a cutoff of around PI of around 7, with transitional behavior between around 3 or 4 and 7. Armstrong and Malvik kind of did a nice literature review and brought in the concept of the fines content, and whether the fines are enough so that the fine matrix is controlling, even if there is sand, and sort of regardless of the PI. And then for CPT liquefaction analyses, we use a common cutoff of I sub C of 2.6, where if you're greater than 2.6, it's typically clay-like, and less than 2.6 is sand-like. There are some sites that have different characteristics that if you compare the PI of soils, you might find that your actual cutoff I sub C might be a little lower or a little higher. So some site-specific adjustment to this is sometimes warranted. And then there's a new system called the Delta Q system that's been proposed by Say et al. 2021. This is relatively new and has a a new parameter that can be used to divide between liquefiable and non-liquefiable sites. So that's the composition side. So next is the state and the loading. I think a lot of you are probably already familiar with this, where we have a loading side, which is the cyclic stress ratio. It's based on the earthquake loading and the stresses in the soil that are going to be imposed on elements of soil with depth. We have the peak ground acceleration. We have total stress divided by effective stress. We have the R sub D factor, which accounts for the compliance of the soil column and the participation of the soil column in the inertial loading at depth. And then we have a magnitude scaling factor that accounts for the cycles of the number of cycles in the earthquake given the earthquake magnitude. And finally, an overburden stress correction. So this gives you basically a normalized cyclic stress ratio, or CSR. That's the driving stress or loading for your soil. And then we have a resistance ratio, and we can evaluate this based on laboratory testing. But because of difficulties with sampling, obtaining samples that are undisturbed, and because we have very well correlated and calibrated field data from many case histories, we're able to develop estimates of the cyclic resistance ratio based on penetration resistance, like the CPT tip resistance or the SPT blow count. So once you have these two parameters, the factor of safety against liquefaction is simply the ratio of those two parameters. And the cyclic resistance ratio curves that you see here are ones that have been proposed, based on evaluation of different case studies. So the consequences, what are the consequences? So we have surface manifestations. That's when we have ground cracking. We have the liquefied soil ejecting up to the ground surface and disrupting the surface, causing more settlements because whatever volume is ejected is subtracted from below grade. We have loss of bearing capacity, where if the soil liquefies, it becomes less stiff and less strong, and any loading, either static or inertial, that's imposed upon the liquefiable layers can undergo loss of bearing capacity and settlement. This is a photograph from the El Mayor Cucapá earthquake in 2010, where this building punched about 3 feet into the ground after losing bearing capacity from liquefaction. We have other kinds of settlements. We have volumetric settlements, where when the soil liquefies, the excess pore water pressure is generated, and then as the excess pore water pressure is dissipated, the soil compresses, similar to the way a clay soil would compress with excess pore water pressure generated by loading. But this settlement happens relatively rapidly after the earthquake because the hydraulic conductivity of the sand is relatively high. And you can see an example here from the El Mayor Cucapá earthquake, where there was a building. The building was founded on piles that extended down through the liquefiable layers. At this location right here, where there was a pile cap and the floor slab draped up over the top of the pile cap and was supported by it. But down here, over here, the slab is just right at grade. And let me make sure that I have a highlighter so that you can see. Over here, the slab was right at grade, so it was didn't have any treatment of the slab, and the slab settled. So you can see the slab settled about 6 inches. The building structure itself was just fine. It was supported on piles and didn't undergo really any damage, but the whole ground floor had to be demolished because of the slab settlement. Then we have lateral spreading, which occurs when we have like a free face or a sloping ground, where the soil sort of ratchets sideways with cycles of loading in the down slope or toward the free face direction, and that can develop irregular ground cracking and displacements in the ground, generally with increasing or decreasing displacements as you move further away from a free face. This happened to be a house that was intersected by one of the lateral spreading cracks from a free face condition that was about 100 feet away or so. And basically the damage was so extensive, this house had to be demolished. And then finally, we have flow failures. So this is the classic example from the Lower San Fernando Dam from the 1971 earthquake, where it underwent a massive flow failure. There was just a few feet of freeboard left in the dam, fortunately, because the reservoir was not at the maximum pool level, and it just barely averted a massive catastrophe of release of water downstream. So these are the kinds of hazards that we want to concern ourselves in terms of their effect on our engineered structures. So how can we mitigate liquefaction? I'm just going to go through some of the most common ground improvement techniques. And when we think about ground improvement techniques for liquefaction mitigation, we like to think of them in terms of their effect on those three aspects of soil liquefaction: composition, soil state, and loading, or the first two aspects rather of soil liquefaction hazard analysis. So composition, we can alter the composition of soil by solidifying it. So we can do that through various grouting methods. We can change a sand into a sandstone, basically, and make it non-liquefiable. Soil state, we can change that to make the soil denser. So we can do that through various techniques of compaction techniques. And then loading, we can alter the loading by reinforcing the ground and having the ground improvement take the shear loading and shielding basically any soil, in situ soil that's between the ground improvement from receiving those higher seismic loads and therefore mitigating liquefaction. So here are a few techniques. This is vibrostone columns using the bottom feed method. This is where we have a vibratory probe. There's a hopper. We put generally clean crushed gravel down through the hopper. It goes into a tube that ejects the gravel at the bottom. The vibratory probe is then compacting and pushing the gravel out and sideways. It's compacting the stone, and it's compacting the soil around the column. The end product is densified soil between the columns, and then a very dense, stiff column, or set of columns or array of columns that can reinforce the soil, carry more vertical loads, and reinforce it and shear against the earthquake. The relative cost of this method is low, and the mitigation mechanisms that we're talking about here are densification and reinforcement, but the reinforcement is more minor, while the densification is the primary mechanism. Then we have vibrocompaction, which is a similar technique, but instead of gravel backfill, we're using typically the existing sands or clean sands. This method requires that it's a little less flexible in terms of the materials that are suitable for it. It requires kind of clean sands with very little fines, probably less than desirably less than 5% fines. But it's got a low cost and can be a pretty effective mitigation technique for the right site conditions. Then we have deep soil mixing. So deep soil mixing is a method where we use a drill rig that's equipped with a mixing tool. We pump a neat cement grout, sometimes has other additives in it, but that neat cement grout is ejected at the tip of the tool, and then the mixing blades mix it up with the soil, and we create soilcrete. So we can combine these columns to create panels and grids, but basically you're changing the composition of the soil from a soil, a sand or a silty sand, into a soilcrete, which is kind of like a sandstone, weak sandstone type of material, with compressive strengths that are range from on the order of 100 psi to maybe even over 1,000 psi in some cases. One thing to keep in mind is that this technique generates whatever grout you put into the ground is basically spoils that mixed soilcrete that comes out of the ground. So generates generally about 35 or so percent spoils that need to be dealt with, disposed. They're typically a good engineered fill type of material. They're cement treated soil and can be broken up and compacted to form nice structural fills. The liquefaction mitigation schemes in this case are solidification, so anything that you actually treat directly is solidified, and then reinforcement. You're shear reinforcing the ground, and I'll talk about that in a minute. Keep in mind that the soil between here hasn't been compacted or densified. It's still in its original in situ condition, but that's okay because we deal with it. We mitigate that by the reinforcing effect. Jet grouting is similar, but instead of a mechanical mixing blade, we're using a high velocity jet stream of grout to erode and mix with the soil. It produces a similar type of soilcrete. It's generally a higher cost, so it's usually used in a more precise way or for very deep layers where the economics can be justified. Compaction grouting is a method where we drill down and we inject a low slump grout into the ground. It expands and forms bulbs. The expansion of the bulbs statically compacts the ground around it. We can put these things in arrays below the ground, and using, in some cases, pretty small equipment, types of equipment that can fit within structures and basements and small areas like that. The one thing you have to be careful of with compaction grouting is that it needs a sufficient overburden stress to allow the expanding grout bulbs to compact horizontally instead of heaving the ground. So typically that's around 10-15 feet or so of overburden. If you need to treat soils that are shallower than that, then compaction grouting is, unless there's some way to to place some temporary overburden during the treatment, then compaction grouting is probably not the best technique. So deep dynamic compaction is a method where a weight is lifted up to 100 feet over the ground. The weight can be on the order of 10 to 30 tons, and it's dropped repeatedly to compact the soil down to depths of around 30 feet or so is where typically the maximum treatment depth is. So this is a method that is the relative cost is low, but there are noise and vibrations, so it's typically only used in areas where you can set back far enough from existing structures and people that would be impacted by the noise and vibration. So this provides you a little summary of these different methods I've covered, whether they're working by densification, reinforcement, or solidification, the types of soils that they're generally effective in, sort of relative cost relative to each other, and then the relative frequency of use, at least as I see it in the Western US where a lot of this work is done. Okay, so ground improvement design. So again, we're talking about reinforcement and densification as two of the main methods of mitigation. So if I have a site that is currently liquefiable and it has a cyclic stress ratio in this red zone, which is greater than the cyclic resistance ratio, that means it's going to have a factor of safety of less than 1. And I want to get it out of the red zone into the green zone where it would have a factor of safety of more than 1. So if I go downward, that means I'm reducing the cyclic stress on the material, and that's accomplished through reinforcement. If I go to the right, that means that I'm making the blow count larger, or basically densifying the material, and that means that I'm densifying, using densification to achieve the improvement. So as mentioned before, vibrostone columns are a method where we can densify the soils. Generally, you get more densification closer to you are to the column. So designing such a program is a matter of figuring out what spacing you need in order to achieve the density, between the columns that you need to, achieve your seismic performance objectives. And so different contractors will have different equipment and means and methods, and the spacing of the stone columns is generally best left up to the contractor to evaluate from a design build perspective. Each one has its own sort of way of estimating the improvement that they'll be able to achieve. Compaction grouting is another densification technique. There's a nice paper by Boulanger and Hayden from 1995 that evaluated several case studies, most of them from old Hayward-Baker projects, where you have the mean net grout take on the x-axis and the penetration resistance on the y. So original ground condition is here at 0 before the grouting was done, and then after the grouting was done, depending on the amount of grout that was injected, you saw an increase in the penetration resistance, either SPT-N or CPT tip resistance. So you can use charts like this to sort of figure out how much improvement you might see depending on the amount of grout takes, or the area replacement ratio of the grout, as we like to call it. On the left, we show a little example case study from a project back in 2013, where the original blow counts are down here. You see in the 0 to 20 sort of range, and the post-improvement blow counts are up here. They're all in sort of the 20 to 50 range. And one thing you'll see here is that there are mean values that are calculated based on a moving average that we used in the spec for this project. I like to emphasize that when we're doing earthquake engineering, just like with any geotechnical engineering, there's always variability in the soil. And we don't want to design for the very lowest blow count, because that's not really representative of, the overall soil mass and the average sort of properties that we would need and that we would rely on in the design. So we shouldn't set specs that are based on the very lowest blow count that you will ever achieve in a project. That's why in this project, we were using this running average mean to make sure that that running average was greater than a threshold value, which in this case was 25. So if you're out there and you're writing specifications for projects, I encourage you to, either use an averaging scheme so that the contractor doesn't have to, one blow count can, cause a trigger, remedial action, when it doesn't really matter as long as your averages are okay. So while densification is a really effective technique, it's only effective in certain types of soils. And the reason for that is that the densification process during ground improvement is typically happening below the groundwater table in saturated soils. And when those soils are saturated, you have to have enough permeability in the soil for the water to be able to dissipate out and the compaction process to occur. And there's basically it's the same reason that you can't, that it's difficult to compact and a saturated clay soil in the field with conventional surficial compaction equipment. It's the same reason why it's difficult to compact a fine grain saturated soil with ground improvement. So there are criteria here I show you based on gradation on the right side. Basically, if you have 25% or so fines or more, maybe 30% fines, then we start having some real difficulty compacting that material, unless we do something special like put in some wick drains to shorten the drainage pass and allow us to compact the material with vibratory equipment. Between 25 and 5% is kind of intermediate, so we get some intermediate results, and then anything less than 5% is very readily compactable, and we'll do a great job compacting that. In terms of CPT, above I sub C of around 2.4, that's getting to be clay enough and fine grain enough that we'll have difficulty compacting that. Below I sub C of around 2.05 or so, no problem, it's very compactable, and there's a sort of transition zone in between. Talked about densification now with shear reinforcement. There have been some early efforts and research that made a assumption of strain compatibility between the ground improvement elements and the surrounding soil. And that was used in the 70s and in the late 80s and 90s to evaluate the reinforcing effects. And there's been more recent research done at Davis and UC San Diego that has shown basically that that strain compatibility assumption is incorrect. So when we look at these elements tend to go more into bending instead of simple shear strain. And when we look at those effects and incorporate those effects, as was done by Ramaggi et al., then we get the curves more like this. So this R sub RD is basically, you can think of it as a reduction in the shear CSR that you're going to see when you put the ground improvement in the ground. So this chart shows that, typically with stone columns, we're in the 10 plus or minus % area replacement ratio. That's the area of the total area of the stone columns in plan divided by the total area. And so, at 10% or so, and a G sub R, that's the ratio of the shear stiffness of the stone column to the soil. So the stone column is about 5 or 10 times stiffer than the soil. In that range, we're only getting about a 5% reduction in the cyclic stress ratio. So that's not very significant. That's why this is a sort of minor part of the stone column design. But on the other hand, with soil mixing grids, when we arrange them in grids like this, we get these very strong and stiff sort of shear walls that are very effective in actually shielding the soil that's in between them from shear stresses. So with DSM grids, we're typically talking about 30 to 40% area replacement ratio. We're talking about shear stiffness ratios on the order of 20, 30 or so. And there we're seeing an 80% reduction in the loading on the soil between the columns. So that's very significant. So settlement from liquefaction. So we talk about these mechanisms that we need to design for. We can have bearing capacity. We can have settlement due to bearing capacity loss. We can have settlement due to the reconsolidation consolidation compression of the liquefiable soil at depth. And we need to account for both of these mechanisms. So when do we need to consider bearing capacity? I read a lot of geotechnical reports, and I like to emphasize this because not all geotechnical engineers think enough about bearing capacity. Everybody thinks about settlement, but bearing capacity is probably an even more important concern when you're talking about liquefaction hazards and ground improvement design. So if you run a 2-layer bearing capacity analysis with a method like Meyerhoff and Hanna, you'll find that if you're about 2 or 3 footing widths below the bottom of the footing, below that, if the liquefiable layer is deeper than that, then generally it's not going to have a big impact or reduction on the bearing capacity. But if it's within this zone, then it's something that you ought to take a look at and design for. And when we do stone columns, hopefully it's a clean enough sand that we can densify it and make it non-liquefiable so that we don't have any bearing capacity concerns at all. But sometimes we can densify it a little bit, or there might be a thin layer that's not densifiable but still liquefiable. And so if we leave any liquefaction in the ground because of practical restrictions, then we need to do a bearing capacity evaluation that includes the reinforcement of the stone columns and the liquefied residual strength of the soil. With soil mixing grids, it's a little easier because we generally can design the soil mixing to readily take all of the building loads and support the building loads without any reliance on the soil between the soil mixing elements. So in that case, even if you lost all support from the soil, generally we're designing already for the soil creep to take all of the loads. So bearing capacity is just a matter of checking the crushing strength of the DSM when the seismic bearing pressures are applied. Okay, so for the deeper layers where we're concerned mainly with the volumetric settlements, the post-liquefaction pore water pressure dissipation settlements, we use these kinds of relationships typically for liquefaction settlement estimations. This is from Zhang and Robertson. And the post-liquefaction strain, which is on the y-axis, is found by knowing what the CPT tip resistance is on the x-axis, and then the factor of safety against liquefaction in these contours that are drawn here. This was based on the work of Ishihara, Shimini and Ishihara from 92, and extended to the CPT by Zhang and Robertson. So if I have a site that, say, has a factor of safety of around 0.8, 0.9, a tip resistance of around 80, if I reinforce that site, what I'm doing is I'm decreasing the seismic load without densifying the material. So the tip resistance is staying the same, but I'm reducing the seismic load, which means I'm increasing the factor of safety. And I'm going to try to take my site from here, which is 2.5% or so volumetric strain, down to something that's lower. If I am densifying the site, that means that I'm increasing the tip resistance by densifying. So I'm going in the horizontal direction. But when I densify the site at the same time, I'm also increasing the factor of safety against liquefaction, because a denser site has a higher cyclic resistance ratio. And so I'm going to increase my factor of safety. So I'm going both laterally and vertically when I densify the site. So here are some practical design examples. This is, I know there's a lot going on this slide with these plots, but this is the software that we use to run liquefaction evaluations and to make predictions of improvement due to our ground improvement design techniques like stone columns or deep soil mixing. So here we are at a site. The gray line that you see here is the CPT tip resistance before we do anything, and the orange line is the tip resistance after the ground improvement. So first of all, we look at the I sub C chart. So this is a pretty clean sand site. The I sub C is mostly around 2. So this is a densifiable site. This is a site that we can compact with vibro equipment. There's a clay layer in between here that is not densifiable, and we won't plan to try to improve that with other than reinforcing it with the stone columns. So as you can see, because it's densifiable, our predictions based on our equipment and methods shows that we can just about double the tip resistance from where it started to where we think it will be when we're done. The red line is the cyclic stress ratio without any ground improvement, and then the dashed red line is the cyclic stress ratio with the R sub RD reductions, which is, as I mentioned before, it's probably around 5%. So we're reducing the cyclic loading, the earthquake loading a little bit, but that's not making that big of a difference. What's really making a big difference is going from the cyclic resistance ratio way down here in blue to the post-treatment one with the denser material, way up here. So by doing that, you can see that we're increasing the factor of safety from around 0.2 or so up to, in some cases, over 0.1, but some cases it's still below not 0.1, but 1. So that may or may not be okay. We like to design for performance. So as long as this soil down here, which is still considered liquefiable, has the decrease in the settlement is sufficient, then maybe that performance can be okay. We don't have to eliminate all liquefaction. We can do that, but it becomes very, very expensive. And why pay for something that you don't need? So you can see my settlement estimation from volumetric settlement's gone from a little over 3 inches down to 1.3 inches. That's sufficient for a lot of projects. Over here on this plot, this is the residual undrained shear strength. So it started off, can't see it, but it was around 400 PSF. That's pretty low strength. It's fairly deep. It's 25 feet below the ground surface where we have those strengths. So if we had a small footing, it probably wouldn't be affected by that if the footing was only like 6 feet in dimension. But you can see that after I do the densification, then I've densified it enough that I get to the point where the drain strength is actually higher than what the undrained shear strength predictions would be. And that's when I get this diagonal line, it means I'm capping that strength at the drain strength. So I've made the strength higher, I've reduced the settlements, I haven't eliminated liquefaction, but this is a successful design that would perform well for many sites. So here's the site where stone columns are not a good choice, because you can see the I sub C is bouncing around in the silty range. So this is a site with a lot of silty material. There's very limited densification that occurs. There's only a minor decrease in the cyclic stress ratio. I still have large settlements, and the shear strength, the residual shear strength is still low. So I tried stone columns, but it doesn't really, not very effective at this site. But if I apply deep soil mixing, I'm not going to densify the site. But what I really do here is I take the cyclic stress ratio and I reduce it a considerable amount. That makes the factor of safety above 1. And reduces the settlements significantly. And you really would have no settlements to the structure because it's supported directly on the DSM. Okay, we're running a little short on time, so I'm just going to go through this real quick. We can use DSM to make buttresses and stop lateral spreading. There we have to check the stability of the material with limit equilibrium analysis and overturning and sliding. We have to look out for the edge stability if the liquefiable material pulls away and you have a structure sitting on it. For some projects, some bigger projects where we have there are more critical projects, we're using numerical methods like FLAC models to predict the stability of the DSM buttress. Is a very effective and rigorous way of making those evaluations. And then finally in here, I have some information about shear wave velocity changes and site changes. So you can't use a simple area weighted method to estimate shear wave velocity changes. You need to use these methods I've cited here by Raimaggi, Bollinger and Shao and Nguyen et al. And you can get significant increases of the shear wave velocity with DSM because of that shear reinforcement. With stone columns at typical replacement ratios, you may be only looking at 10 or 20% increase in shear wave velocity from the original condition. And QA/QC is also a really important aspect. Most of our rigs are instrumented to measure a bunch of different parameters like the amperage going into the work and when we use vibrators, and the diameter of the columns that we produce. And then we need to measure the post-improvement tip resistance or SPT blow count after the work is done to make sure that we get the densification that we were expecting and relying on in the design. With DSM, we're talking about taking grab samples, doing coring to check the quality of the cores, doing compression testing, and making sure we meet all those parameters. I'm not going to really talk too much about rigid inclusions, just that there's some ongoing research that's underway to evaluate these things because they're relatively slender and brittle, and so their use for liquefaction mitigation is really questionable at this point, and further research is needed. Okay, so I have some a bunch of the references on here for your use, and I don't know if we'll have any time for questions, but if there are questions that we don't have time to address, then I'm happy to follow up with by email.
James, you still have 10 minutes left.
Oh, 10 minutes.
Yep.
Okay, then we do have time for questions.
Okay, we have a question from YouTube. Earthquake magnitude and max acceleration can modify greatly the liquefaction analysis results. In your experience, what influence can these parameters have on the ground improvement method to use?
So in current practice, I know that there's a good amount of research that shows that there can be a significant change to ground motion characteristics, stiffening of the site and an increase in the high frequency content of the ground motion resulting from ground improvement techniques. In current practice, the way that it's handled is that the analyses are done with the parameters of the site, assuming that the site, that it's a virgin site that doesn't have the ground improvement. On the other hand, if if you like, and especially if you're counting on trying to change the site class based on the change in the shear wave velocity, you can account for that with these relationships to change the shear wave velocity, reevaluate VS30 or your site response analysis, and come up with changes in the spectral accelerations that you could use for design.
Okay. Our next question is, what are your opinions on EQ drains?
Yeah, so earthquake drains is a technique that I didn't cover here, but it's basically a method where you install with a mandrel a sort of larger diameter wick drain. It allows for water to be drained out during the earthquake loading so that the pore water pressure doesn't build up. In some parts of the country, it's very commonly used and effective. We don't use it quite as much in the Western US where I do most of my work, just because with dirty soils and a high level of earthquake loading, it can be difficult to make them work. We in California and the Western US, we're using peak ground accelerations on the order of, for design, on the order of 0.6 to 1 G, and it's difficult to make that technique work a lot, but it can work in some cases, and it can also be very effective in supplementing another ground improvement technique, like having stone columns and earthquake drains at the same time.
Okay, we have a question: how to mitigate liquefaction potential below a large diameter structure like a water storage tank without disturbing the existing foundation?
The kinds of things that you could look at are, number one, compaction grouting. If the layers are deep enough and there's enough overburden stress, you might, you would prefer to take the tank out of service and be able and core through the slab to do the injections. But it is possible also, we've done work before with horizontal directional drilling. You can come in from the side and do the compaction grouting from the side. You could also consider jet grouting, and those would be the primary techniques that might be applicable there, other than like underpinning with deep foundations. It really depends on the details of the site and the project. If you have any particular projects that you would like a ground improvement contractor design engineer to take a look at, please feel free to reach out to me afterwards.
Okay, our next question is, what is the best and most robust constitutive model for liquefaction modeling in numerical methods?
That's a pretty loaded question. For me personally, I mean, the ones that I see used in practice the most are, I think PM4 sand has become probably the most widely used and popular. The UBC sand model is used a lot. The URS model is still used a lot. The UCSD soil models, the UCSD models are used here and there. My personal preference is typically PM4 sand and PM4 silt. Just has a lot of flexibility. It's very rigorously implemented in FLAC. It's got a lot of research and practice application behind it. So that's typically what we prefer to use.
Okay, doesn't look like we have any more questions at the moment. Did you want to add anything, or?
I guess just that, yeah, if you have any follow-up questions, or if you have a particular project that you're not sure what ground improvement technique might be suitable, or whether ground improvement is suitable at all, feel free to reach out to me. My email address, I believe, is here. So james.gingrey@keller-na.com. Yeah, and I would be happy to try to help out.
Thanks
Great,
very much
thank
for, I'm sorry.
Sorry, I was just going to say great. Thank you so much. And if there are no further questions, I'll go ahead and end the session.
Thank you very much for this lunch and learn session.
Thank you. Appreciate it.
Everybody have a great afternoon.